In this video, I will talk about Bernoulli's principle. The Bernoulli's principle is based on the ideal fluid. Again, I will summarize what is the ideal fluid. The ideal fluid must meet the following condition. It must be incompressible. What does this mean is the density of the fluid must remain constant at any point. It should not change with the time or with the position. Okay, at any point if I measure the density, then it must remain the constant, and it must remain constant not only in the position. Let's say for example at this point, it must remain constant. And even if you choose one point, then at any time the density must remain the constant. That means it should not be a function of time, it should not be a function of position. Okay, the density must remain constant. The non-viscous, what is the non-viscous means? That means the viscosity of the fluid must be zero, or must be very very minimum, almost zero. That what does this tell you is that there is no internal friction when the fluid moves. If you look at the fluid here, let me draw here. If a fluid move, then it moves layer by layer here, layer by layer, and there is internal friction in between them. So the ideal fluid means that there is no any internal friction between the each layer of the fluid, or in other words we can say that there is no any retarding force on the fluid. And the other thing is the steady flow. Steady flow means the velocity and pressure does not change with the time. Now let's say for example the fluid is moving through this tube here. If I look at any point, the velocity, the pressure is independent of time. That means it does not fluctuate with the time. That we call as a steady flow. And the streamline flow means the fluid particles moves in a smooth continuous line, and the path of the two particles, that we call as a streamline, never cross each other. If they cross each other, then it will no longer be a streamline flow, rather it will be a turbulent flow, and the energy conservation will no longer be the valid. Okay, so now based on this one, let's derive the Bernoulli equation. So here we're going to derive the Bernoulli equation here. So we have chosen a pipe here. It could be in any shape. So here is a pipe here whose cross-section area is A1 at this point, and the cross-section area is A2. And as I mentioned, it could be in any shape. And the pressure or the force, now let's say the force at this point is F1, and at this point it is F2, because there must be some sort of the force here. If you simply let it open on this end, then this force could be due to the atmospheric the pressure, and the pressure at this point is P2, and this segment is at a height of Y1, and this segment is at a height of Y2. So what does the Bernoulli equation tell you? That the total amount of work done, the total amount of work done in moving a fluid from point 1 to point 2 must be equal to the total change in mechanical energy. Okay, the total amount of work done must be equal to the mechanical energy, which is the sum of kinetic energy plus potential energy. And I am writing down the external here. That means the net external work done must be equal to the change in kinetic energy plus the change in potential energy. This is the conservation of energy, and you might have studied this one in the work energy theorem. Okay, so the total amount of work done is equal to change in kinetic energy plus change in potential energy. The delta U means the change in potential, delta K means change in kinetic energy. That's the equation I have written down here. So now the goal is to find out how much work will be in moving a tiny segment delta of fluid, or the delta V volume of the fluid from point 1 to point B. So the total external work done is equal to the amount of work done at this point and this point, W1 plus W2, because there is a force on each end here. So let's find out the amount of work done. What is the work done? How do we define the work? Work is the force times the dx vector here. This is a dot product here. Okay, so that's the work. So if I look at these two, the force and the displacement at this point, the force and the liquids are moving in the same direction. So that means the angle between them is cosine 0, which the angle between them is 0, so cosine 0 is 1. So that means if you write down force times dx vector, it will be F times dx, because the angle between them is 0, so cosine 0 means 1. And why I'm calling the cosine here? Because by definition the dot product is defined as A vector dot B vector is AB cosine theta. Okay, if they are moving in the same direction, the cosine theta will be cosine 0, which means it is 1. And now if I look at the other end, the force is acting in the opposite direction, and the volume and this tiny segment is still moving in the forward direction. So that's the reason I have chosen the negative sign here, the negative F2 times dx2. So now I have written down the force. If you look at the pressure is defined as the force divided by the area. So force would be equal to the pressure times area. That's exactly the thing I have written down here. At this point, the force is equal to P times A1, and at this point A, it will be P2 times A2. This is 2 here. It looks like A, but this is 2. P2 times A2. Okay. So now look at these two terms, A1 dx1. What does this mean? A1 is the cross-section area and dx1 is this length here. So if the product of area and this length gives you the volume of this tiny segment here, or tiny portion here, that's the volume here. And the same way, cross-section area A2 and this tiny segment here is dx2 is the volume of this area here, that's the V2. And as I mentioned here, we're finding the work done in moving this volume from point 1 to point B. So the volume, this volume here, this tiny segment volume, this one and this volume is exactly the same. So V1 and V2 is exactly the same because we are moving the same fluid from point 1 to the point B. So V1 and V2 is the fluid volume, and I'm assuming V1 is equal to V2 is equal to V. Okay, just to make the calculation better. So I got P1 minus P2 times V, and again the density is equal to mass per unit volume. So volume would be equal to mass divided by the density. So that's the equation I have written down here. P1 minus P2 times m divided by the density. Rho is the density of the fluid. And also, if you look at this equation, this might sound familiar for those who have taken the chemistry classes or the thermodynamics classes. The P1 times V is the work done. So now let's plug this equation number 2 into equation number 1. Okay, so instead of external work done, I'm writing down P1 minus P2 m over density. That's what I have. And now I have delta K plus delta U, which is kinetic energy and potential energy. So what is the kinetic energy formula? First, let's understand delta K means. Delta K is the change in kinetic energy. That means kinetic energy at point 1 minus kinetic energy at point 2 minus kinetic energy at point 1. Similarly, delta U, which is the change in potential energy, means the potential energy at point 2 minus potential energy at point 1. Okay, so that's what I have written down. What is the equation for the kinetic energy? If you recall, kinetic energy is defined as 1/2 mv squared. Okay, so that's what I have written down here. If you look here, kinetic energy is 1 half mv2 square. That means this is the kinetic energy of the fluid at point 2, and this is the kinetic energy of the fluid at point 1. And what is m? M is the mass of the fluid. The mass of the fluid in this tiny portion here, or the mass of the fluid in this tiny portion here. Okay, and the potential energy, this is the gravitational potential energy. So how do you define the gravitational potential energy? This is mgh. Mg, and the h is chosen from a reference point. If you look at this is a reference point, or this is a reference point. The height of the fluid is, we always measure from the center, is y1, and this one is y2. So that's what I have written down, mg y2. This is the potential energy at point 2, and this is the potential energy at point 1. And now if you look carefully, that in each term we have the mass. So this mass, this mass, this mass, this mass, and this mass cancels out. Okay, so the equation will be a little bit more simpler now. P1 minus P2 divided by rho, because the mass is cancelled out. This mass is cancelled out, half V2 square. This mass is cancelled out, half V1 square. This mass is cancelled out, and we have this equation. And then we need to bring all one term on one side. So with one subscript, so P1, I'm taking out this one, and we're multiplying both sides by rho, which is the density. So I will be left with P1, okay? And then I see this one term here. This has a negative, so if I bring on the other side, it will be positive, and I'm multiplying by rho. The same thing here, this has a negative. If I bring to the other side, it will be positive. And the same, now if I bring P2 on the other side, it will be, this is negative. If I bring it to the other side, it will be positive. So that's we get here. So what you see here, P1 half rho V1 square plus rho G1 is exactly equal to P2 plus half rho V2 square plus rho Gy2. What does this tell you? That this tell you that this term is a constant term. It does not fluctuate from point 1 to point B. And this idea, or this equation, we call as a Bernoulli equation. And this is exactly based on the conservation of energy. Okay, and if you look at this pressure here, this pressure is the total absolute static pressure. This is the dynamic pressure, and this is the hydrostatic pressure. So this is the hydrostatic pressure, because this is based on the height. This is the dynamic pressure, because it is related with the velocity, and this is the static pressure, okay? And these three pressure together, the sum of all this pressure at any point of a fluid, of an ideal fluid, must remain constant, and that is the Bernoulli equation. Okay, so now let me give an example here. Now let us consider again a pipe where cross-sectional area changes from point 1 to point 2, but the height remains constant. So what happens to the velocity? What happens to the pressure? So you can see as the cross-sectional area has reduced, if you recall the equation of continuity, if the area has reduced, what should happen to the velocity? If the area reduces, then the velocity must increase, because of this continuity equation. A1 V1 is the velocity, is equal to A to V2. And if you look at this one, A2 is smaller than A1. A2 is smaller than A1, so V2 must be greater than V1. That means at this point, the fluid must move faster. And as I tell, like a smaller the cross-sectional area is, the fluid moves faster. And now, what happens to the pressure? Will the pressure go up or pressure go down? That we can get that answer from the Bernoulli equation. So let's use the Bernoulli equation one more time. So P1, that means I'm writing down this part here, P1 half rho V square rho GH is equal to this portion here, P2 half rho Vt square plus rho GS2. And in this case, height does not change. So this term and this term cancels out. So we have P1 plus half rho V1 square plus P2 plus half rho v2 square, because this term and this term is cancelled out because height is not changing. Okay, so now we have already found out that the velocity at this point is greater. The v2 is greater. v2 is greater. If v2 is greater, that means the p2 must be smaller. p2 must be smaller. That's what we get here. Because if this term is greater, then this term must be smaller to balance each other. Okay, so what we got from the Bernoulli equation is that the pressure at this point where the velocity is faster, the pressure is small. Just remember this one. When the fluid moves faster, the pressure is smaller, or there is a low pressure. Or in other words, you can see when the streamlines are closely packed, there must be a low pressure. Let me give you an example. Another example here. In this case, what we have assumed here is the cross-section area does not change, but the height is changing. So if you recall equation of continuity, a1 v1 is equal to a2 v2. Cross-section area does not change, so that means the velocity at this point must be equal to the velocity of the fluid at point 2. So v1 and v2 must be exactly equal. And now let's apply the Bernoulli equation to find out what happens to the pressure. So I'm writing down the Bernoulli equation, and in this case the velocity does not change, so this term and this term must cancel out each other because the density is constant, because we have assumed the ideal fluid. This density does not change, and v1 and v2 are equal, so this term and this term cancel out. And now we have this term here. And if you look at this picture here, this diagram, h2 is clearly greater than h1. If this term is greater, if this h2 is greater, this term must be greater. If this term is greater, then the p2 must be smaller to balance each other. So we see that the p2 is smaller. That means the p2 at this point is smaller than p1. Okay? So in this case, the velocity is the same. The velocity is the same, but the pressure is smaller, and this happens because the gravitational potential energy is greater. Okay, so the Bernoulli equation relates the gravitational potential energy, kinetic energy, and the pressure. Okay, so in the first example, when the if the potential energy is constant, and if the cross-sectional area is smaller, then the velocity must be greater and the pressure must be smaller. And in this case, the cross-sectional area is the same, but the potential energy is greater, so the pressure must be smaller. Okay, so this is it from the Bernoulli principle, and then next video I'll give more examples about the Bernoulli principle, or we can say application of Bernoulli principle. So thank you.